Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about how to fit parametric models to data. In previous videos we have defined several parametric distributions, including the binomial, the geometric, or the Poisson. In order to use those distributions for probabilistic modeling, we have to estimate their parameters from data. And that's what we're going to learn how to do today. Let's get to it. The method that we're going to introduce is called maximum likelihood estimation. The plan is exactly that, to learn how to fit parametric models to data. Let's take a look at our motivating example where we were modeling the free throws shot by Kevin Durant in the NBA. We had this data set where we had the length of 377 streaks obtained from about 3,000 free throws. And what we wanted to do was to model the length of the streak. So we wanted to basically estimate what is the probability that Durant is going to make 10 free throws in a row or 15 free throws in a row. We were not super satisfied with the non-parametric way to do this, which used the empirical PMF. And because of that, we designed a parametric model that looks like this. Okay, just to be clear, this parametric model depends on a single parameter theta. And it says that the probability that we're going to see a streak of length s obviously depends on the parameter, but given a fixed value of theta, it's going to be equal to theta to the s times 1 minus theta. And if you remember, theta represents the probability of making each free throw. I recommend that you go back to the video on the geometric distribution if you don't remember that very well. But let's assume that we have a parametric model that we have designed that we're happy with. So now what happens? Well, if we look at the data, here I'm showing you the empirical PMF as these black dots, okay? If we just put any value of the parameter, here for example 0.8, chances are our parametric model is not going to be very good. So here the white circles show you the shape of that PMF that we derived if we just set the parameter to equal 0.8. I don't know if you hear the ambulance. I thought maybe, Saturday afternoon New York City would be calm, but I guess it never is. Okay, and if you put another parameter, 0.95, again, here we see that this value of the parameter does not really correspond to the data. So how do we find a value of theta such that we fit the data hopefully as well as we can? Okay, we're going to see how to do this. Let's start by imagining that we only have one data point. Obviously, this will never happen. We're not going to fit a model just with a single data point, but it's very instructive to think what we could do. So imagine that the value of your data point is A. For example, we see that Durant has made 10 free throws in a row. The length of the streak is 10. That's a single data point that we want to fit with our model. We have our parametric PMF P of theta that depends on some parameters theta. How should we choose theta? Well, we should think about what this means, P of theta at A. This is the PMF evaluated at the data point that we have seen. Typically, we think of this as a function of whatever we plug into the PMF to get a probability. This tells us the probability that the probability of observing this streak, the length of length 10, given the parametric model, assuming the parametric model is correct and assuming that value of theta. But now we can vary the value of theta. We can interpret this object as a function of theta where the data point is fixed, because that's the data point that we've seen. Okay, we are choosing the parameter given a fixed set of data, right? So that makes sense. So now how would you set theta? It makes sense to try to maximize the probability of the data point that we've seen, right? The logic being we've seen it, so the probabilistic model that we want to fit should give pretty high probability to what we've seen. Okay, that will make it correspond closer to the data. That's the logic. This function as a function of theta, as we will see, is called the likelihood. Of course, we never have only a single data point. right? So what do we do if we have more data? If we have more data, we have to make some assumptions about how the data are related in order to be able to fit the parametric model. In order to do that, we're going to introduce the concept of independent, identically distributed random variables. So as we already saw, there can be several random variables defined on the same probability space. So for example, let's take A1, A2, AN. These random variables are going to represent the data that we're observing and which we're using to fit our probabilistic model. They're defined on the same probability space. If all of those random variables have exactly the same PMF, we say that they are identically distributed. Okay, and the idea here is that we're seeing n data points and we think that each data point comes from the same PMF, which kind of makes sense if we're trying to fit a PMF to the data. PMF is probability mass function. I'm not sure I said that already in this video, but that's what we're trying to do, right? We're trying to estimate the probability mass function of a discrete random variable, assuming a parametric model that we have designed. Okay, apart from being identically distributed, we're going to assume that the data are independent. What does that mean? It means that if I consider the event, the first data point is equal to some value, and the event, the second data point is equal to this other value, up to the event, so this set of n events where each data point is equal to a different value, up to an is equal to whatever value. I said value like 20 times here, but I think you see what I mean, right? Like there's one of these events for each of the data points. As long as those events are all mutually independent, which basically means that it doesn't matter what the first data point is, the nth data point only depends on the PMF. Okay, it's equal to each of the possible values in the range of the random variable with a probability that is governed by the PMF independently from the other data points. This is a pretty reasonable assumption if you're trying to estimate a PMF from data. Okay, so we're going to assume that our data satisfy these conditions. Each of the data points comes from the same PMF and they're all independent. This is a very common assumption, which is usually known as IID, independent and identically distributed. Okay, so now let's go back to our problem. Now we're going to do the same thing as with a single data point. With a single data point, basically what we said is, let's express the probability of observing this data point in terms of the PMF that we're interested in. And it was super easy because it was just the PMF evaluated at that data point. If we have more points, more data, that's not true anymore. But under the IID assumptions, it's very easy to connect the probability of observing exactly those values, which we call x1, x2, xn. These are fixed values. This would be like maybe 2, 7, 53, 27, whatever streaks we observe in our data in the free throw example. Those are fixed, right? And now we want the probability of observing those under our parametric model. If we assume that the data are IID, this probability is a probability of the intersection of several events which are all independent. So it factorizes into the product of the probability of the individual events. But now we're also assuming, apart from independence, that each of these guys has the same PMF, which is the parametric PMF that we're interested in fitting to the data. So now all of these guys are just p theta at x1, p theta at x2, and so on and so forth. So we have this product. This just means that we're taking the product from I equals 1 to n of the parametric PMF evaluated at each of the data points. Okay, that's the probability of observing the data under the assumption that the parametric model holds and that theta is equal to whatever value we plug in here. Okay, so now what we're going to do is we're going to again change our perspective. We're going to stop thinking of this as a function of the data because the data are fixed. We need to choose theta with respect to the data, right? So we fix the data and we are going to interpret this as a function of theta, which we're going to call the likelihood, and we're going to maximize that because the idea is that we want the model that makes the data as likely as possible, that is the most consistent with the data we observe. And that's essentially maximum likelihood. So we have this function of theta that is the probability of observing the data that we observe as a function of theta. Typically, here we're going to be multiplying many probabilities. Imagine if you have 100 data points, for example, and those are numbers between 0 and 1. So this value is going to be extremely small. In order to avoid numerical instabilities, usually what we do is we take the logarithm of that. When you take the logarithm of the product, you get the sum of the logarithms. Okay, so usually we actually deal with the log likelihood function instead. Taking the logarithm crucially does not change the maximum of a function because the logarithm is a monotone function. That's really important because the whole point is that we're going to maximize this with respect to theta to find the theta that is more consistent with the data. That method is called maximum likelihood. So the idea is that given a data set, what we do is we take the parametric model that we have designed and we build the log likelihood function typically under IID assumptions, and then we maximize it with respect to the parameters. And the maximum we call theta ML because of maximum likelihood. We're going to see an example right now where we're going to fit the parameter of a Bernoulli distribution, the simplest possible parametric distribution, to data. Remember that a Bernoulli random variable can be equal to 1 or 0 with probability theta. So its PMF only depends on this parameter theta. Okay, so now imagine that you have n data points here that are either 0 or 1 because we're fitting a Bernoulli random variable to this data. So we're going to derive the likelihood. The likelihood, remember, under IID assumptions, is the product of the PMF evaluated at each of the data points. And now for the Bernoulli distribution, this is equal to either theta if xi is equal to 1 or 1 minus theta if xi is equal to 0. So if we have, I don't know, 10 data points that are equal to 1, we're going to multiply theta 10 times. And then if we have like 5 data points for which are equal to 0, we're going to multiply 1 minus theta 5 times. So basically, we have theta to the power of the number of 1s and 1 minus theta to the power of the number of 0s. And that's the log likelihood function for this data. Remember that this is a function of theta and that the data are fixed. So here the number of 0s and number of 1s are fixed. So now we can plot this as a function of theta. We're going to plot it in a moment. We will see that the values are super small because we're multiplying these values between 0 and 1 many times. So it makes more sense to have a logarithm. Okay, when you take the logarithm of this expression, the products become sums, the powers come down, and you get this. This is how the likelihood function looks like for this data, where you see 60 ones and 40 zeros. Realize that in this case, it doesn't matter in what order we see the zeros or the ones. Okay, that's what it looks like. Realize that the values are 10 to the minus 30, so you don't want to deal with this on a computer. It's better to take the logarithm. The logarithm, so look, the maximum here is here. We'll see why the maximum is right there at 0.6. When we look at the logarithm of the expression, the maximum is still at 0.6 because the logarithm is a monotone function. And now the values are much more similar, much more reasonable, I mean. Okay, the values are much more reasonable. Okay, so that's the log likelihood function. In order to choose theta, we're going to choose the maximum because that is the value of theta for which the data have the most probability according to our parametric model, which makes the parametric model more consistent with the data. So how do we find the maximum of a function that only depends on this single parameter? We take derivatives. This is the first derivative. If you remember, the derivative of log theta is 1 over theta. So we get this derivative. And now we want to check how the function looks like in general. We already saw a picture, which looks good, right? Because it was concave in the picture. let's make sure that this is always going to be concave for any values of n1 and n0. For that, we take the second derivative, and we see that the second derivative is actually negative. So that's really good news, because it means that, and it's strictly negative, which means that there's a single maximum here and the function is concave. So now we can just set this equal to 0 to find that maximum. If we do that, we get that theta ml, the maximum likelihood estimate of the parameter, is equal to n1 divided by n0 plus n1. This is just the fraction of ones, right? Because this is the total number of data. This actually makes a lot of sense, because remember, and it's always good to take a step back and say, okay, what does my parameter actually mean? What does it represent? Does the estimate make sense? Our parameter represents the probability of seeing a 1, and we're estimating it as the fraction of ones in the data. So that makes a lot of sense. And you can see that this is exactly where the maximum was, 0.6, because that's the fraction of ones in the data. All right, so let's go back to our example with the free throw streaks, okay? We had this parametric model that we had defined. I'm going to remind you that the way we defined this parametric model was assuming that the free throws were independent and the probability of each free throw is equal to theta. That is going to be quite important to remember in a moment. But let's look at the log likelihood. Okay, so the log likelihood is just the log of the product of the PMF evaluated at the data that we are seeing, which are these 377 streaks of different lengths. The log, we're taking the log of a product, so that's just going to be the sum of the logs of our parametric model evaluated at those data points. So we plug in our parametric model, that's what it looks like, and now we expand things because we have a log of a product, so it's going to be the sum of the logs, and that's what we get. And now we realize something. We realize that here we have the sum of all the streaks, of the lengths of all the streaks, multiplied by log theta. What is the sum of the length of all the streaks in terms of the free throws made in the data set? Maybe take a moment to think about that. You can stop the video. So if you think about it, if you just put all the streaks together one after the other, you're basically counting all the made free throws. So the sum here of the xi's is just equal to the number of made free throws. And now we're going to have here log of 1 minus theta summed n times. N is the number of streaks. Realize that every time we see a streak according to our definition of streak, there's a missed free throw after it. So n is also the number of missed free throws. We can write this expression. I should have shown you this first. So basically what I was saying is we have this times log theta and then n times log 1 minus theta. And what I just argued is that that is actually the number of made free throws. This is the number of missed free throws. This is important because we have arrived at exactly the same expression as we had for the Bernoulli parametric model. Here I encourage you to take a moment, stop the video and think why this makes sense. And then I'll tell you. The reason why it makes sense is that our assumptions for our parametric model are exactly that the free throws are IID Bernoulli random variables, right? The probability of each free throw is the same, has probability theta, and they're all independent. So these are exactly the same assumptions we made for the Bernoulli log likelihood. So it's natural that we obtain, like in order to estimate theta, which is the probability of making a free throw, we obtain exactly the same estimate, the same maximum likelihood estimate as in the case of the Bernoulli, which is just the fraction of made free throws. Okay, this is telling us that if we want to estimate theta in our model, it's just a fraction of made free throws, which makes a lot of sense under our assumptions. Of course, afterwards, if we want to build the probability of the streaks, we have to use the parametric model that we have designed. It's just that if you try to choose the parameter of the parametric model using maximum likelihood, this is equivalent to just fitting a Bernoulli to the free throws. Okay, hopefully that makes sense. So we just do that. So now theta is just going to be the fraction of made free throws, which is 0.875. And if you plot the log likelihood, this is the maximum at 0.875. I'm also showing you the log likelihood of these two other values of the parameters that we just tried, just to try at the beginning of the video, and we saw didn't really give very good fits. Just to remind you, this is the fit that we got for 0.8. This is the fit that we got for 0.95, pretty bad. Like, you know, this, the circles for 0.8 and for 0.95 don't really correspond to the data that we're observing. And now let's see how the maximum likelihood parameter, like the PMF corresponding to the maximum likelihood parameter looks like. It looks much better. We get a very, very nice fit. In a way, maximum likelihood is implicitly looking for the circles that fit the data best with the constraint that it's still a valid PMF, with the constraint that it still adds up to 1 and has obviously the predefined shape. Okay, so now we're going to do a little experiment just to see, also to think a little bit about what the maximum likelihood estimate actually gives us. We're going to assume, this doesn't happen with the real data, of course, but we're going to assume that we had a situation where the data are generated IID from a model where the true theta is equal to 0.875. And we're going to see if with 3,000 free throws, we would actually get a reasonable estimate of theta using maximum likelihood. It's not going to be exact because the data are finite. So every time you have finite data, you're not going to be able to recover the exact parameter, but we can see how stable the maximum likelihood estimate is. Again, this is synthetic data. The real data, of course, is not generated IID because it's just Durant shooting free throws in the real world. Okay, but here the data are IID because I am generating them in my computer. Okay, so what we see is that this is how the log likelihood looks like. This is the true value. And for 3,000 synthetic free throws, this is how close the maximum is to the true value. So it's pretty close. Okay, actually the maximum was 0.873. Here you can see the model estimate by the parametric model, the circles compared to the true model. Okay, it's extremely close. And you can also see the empirical PMF here, which tells you what the data actually look like. Okay, so with that number of free throws, if the parametric model were true, then we would get an extremely good estimate of theta. This is another run with 3,000 other free throws. Again, we're pretty close, not as close as before, but still. In this case, the theta that we obtain from the data is 0.879. Again, super close. I repeat it again. This is a little bit farther, but still very close. Still a very good estimate. Okay, so this is just to show you that if the data were generated from the true parametric model, maximum likelihood actually would give you an excellent estimate as long as the number of data are not extremely small. However, the challenge is that in the real data, the parametric model makes assumptions that do not necessarily hold. And that's all I got. We have learned how to fit parametric models using maximum likelihood. Thank you very much.